In last lecture, we have used an ideal filter frequency response and then try to realize it by using two techniques. First, truncating an infinite impulse response. Second, delaying the response. These 2 points makes the filter FIR first and second causal in nature. Now FIR is finite impulse response. To get the FIR response, we have used a window function. Wn, which is defined as 1 from 0 to n up to m minus 1 and 0 elsewhere. In last lecture we have used window from minus m to m, but in this class we are using window from 0 to m minus 1 because we have seen to attain the causality we have delayed the sequence. So what we are doing right now in this particular case, we are first delaying the sequence and then multiplying with the window, and so that our window is from 0 to m minus 1. Obviously we have already seen that for a causality, delaying particular response does not alter the magnitude response but modifies the phase response only. So in this particular class we are mostly dealing with the magnitude part, thus we doesn't require to handle that phase part yet. So we have an infinite impulse response sequence which is delayed by m by 2 and the obtained sequence is, the shifted sequence is represented as this HDN, and as we have shifted this particular sequence, our response in which we are interested lies from 0 to m minus 1. Interest response. Now we have already delayed this particular sequence. Now we will use a window function to truncate this sequence most general form of window function, which is defined as rectangular window, is as Wn, defined as 1 from 0 to n, m minus 1 and 0 elsewhere. Instead of starting from minus m, our window is starting from 0 to maintain the causality. Is represented in this particular form from minus infinity to infinity. It has a value of 1 from 0 to m minus 1, and when it is multiplied with HDN with Wn, it gives an output that is Hn. Now this Hn is a truncated sequence. Hn will look like only the selected values from 0 to m minus 1. Thus, then an infinite sequence is truncated into a finite sequence. Multiplication in time domain is equivalent to convolution in frequency domain. So that is H omega is equal to H d omega convolution with W omega. We already knew the frequency response H d omega as it is an ideal filter characteristics. We already knew the ideal frequency response H d omega can be represented as this. Now the important point is, what about the frequency response of the window function? Because this is the function which is truncating an infinite sequence into a finite sequence. This truncation is making that non-realizable filter to be a realizable filter. So this truncation is very important. So we have to think about this particular window function and see how it affects the response of the filter. So Wn we knew is equal to 1 from 0 to n up to m minus 1 and 0 elsewhere. So if we want to find out W of omega, that will be equal to summation n equals to minus infinity to infinity Wn e to the power minus j omega. Now this Wn is defined from n equals to 0 m minus 1 exponential minus j omega. Now this is a finite GP series, so we can directly apply the formula of a GP series, that is 1 minus exponential minus j omega m over 1 minus exponential minus j omega. So if we take exponential minus j omega m by 2 common from the numerator and exponential minus j omega by 2 common from the denominator, will give exponential j omega m by 2 minus exponential minus j omega m by 2 in the numerator and exponential j omega by 2 minus exponential minus j omega by 2. Now these two numerator and denominator forms can be further resolved in exponential minus of j omega m minus 1 by 2 and then sine omega m by 2 over sine omega by. Now this is the frequency response of the window function. Please note that the magnitude of the window function is mod of sine omega m by 2 over sine omega by 2. After magnitude, next is the angle of window function. That will be equal to minus of omega m minus 1 by 2 for sine omega m by 2 greater than or equal to. Please note that omega can have a maximum value in the positive domain from 0 to pi, and by this omega by 2 will give you the maximum value of pi by 2. But with the increasing value of m, you can land in third quadrant also, where sign is negative. For the negative values, the phase will be minus omega m minus 1 by 2 plus pi, as we have already discussed in the previous lectures. Plus pi will be introduced for a negative sign. So in that case, sine omega m by 2 will be less than 0. The frequency response will look like this. From 0, start from 0 and goes up to infinity. One can find out the magnitude of the response is sine omega m by 2 over sine omega by 2, and its 0 values can be obtained when sine omega m by 2 over sine omega by 2 will be equal to 0. Zero crossings we want to find out, because we are interested in finding out the width of the main lobe, that is sine of omega m by 2 should be equal to k pi, where k is equals to plus minus 1, plus minus 2, plus minus 3 and so on. So omega m by 2 is equal to k pi. For the first zero crossing it is 1 for k equals to 1. So it is omega is equal to 2 pi by m. So the first crossing is at 2 pi by m, second is at this side is minus 2 pi by m, and so on. So what does it means? The width of the main lobe depends upon the length of the window. M is the length of the window and width of the main lobe is equal to 4 pi by m. We have used rectangular window in this particular case, so we have find out the width of the main lobe. Now we'll come again to our filter response, that is h omega, that is equal to h d omega convolution w omega. That's mean if we write this particular relation as h omega equals to 1 by 2 pi minus pi 2 pi h d nu w omega minus nu and d nu. So what does it mean? That's mean we have a infinite impulse response, that is h d nu, which is an ideal filter, and then we have a window frequency response we have find out. We'll shift our response over the same axis by a nu from minus pi to pi, and at each and every point there will be a multiplication, and then that integration will give the area under the curve. It will look like the convolution response h omega can be seen from this representation, where h d nu is this window in frequency response and w omega minus nu is the shifted response of the window. Now as nu will shift from minus pi to pi, this particular response of the window will go from this point to this point through this window and give us a desired result of h omega. When main lobe of the window frequency response meets with this sharp transition of the ideal filter, then as the value of nu increases towards pi, the frequency response of the window will pass through this window. A window, or we can say the ideal filter response. Now after this multiplication, the whole multiplications at each and every point will be integrated from minus pi to pi, and we'll find out the area under the curve. Then the convolved response will look like this. Please see this particular case. This is the ideal response. And this we have achieved is the actual response. One can see there is a increment in transition from pass band to stop band. In ideal case, it is a sharp transition, whereas in actual realization, actual response after truncation by using window function, the transition is so much delayed or continuous in nature. Previously it is discontinuous, it is a sharp transition, now it is a continuous in nature. This transition is due to the width of the main lobe. We will again revisit the same diagrams, figures. So please see this particular case. This is here comes the transition. This transition will be sharper as this width of this particular window is smaller. Ideally, it should be an impulse response. Ideally, it should be an impulse just at this particular point. Linear response, right? And this linear response is attributed due to the main lobe width. This main lobe width for rectangular window is equal to 4 pi by m. It can be seen if m is increased. Main lobe width rectangular window in rectangular window is 4 pi by m. If m is increased, then main lobe width decreases. So this is what we want. We want this transition to be as sharp as possible. But there comes a trade-off. If m increases, complexity also increases. As the length of the window increases, there will be much more computation to be performed to obtain that particular result. That's mean ideally m should go to infinity. If m goes to infinity, it is an infinite impulse response. For that particular case, we have a sharp transition. Now it depends upon the application, what kind of application we are looking for. If our application requires very sharp transition, then we'll make m so large that the transition will be very sharp. If our application is, we can afford some kind of transition delay, then we can have m to be small or a moderate number such that our complexity cannot be so high. One thing to be seen, in pass band and in stop band, there are ripples. Ripples in pass band and stop. These ripples are due to the area under the side lobes, and it should be noted, as m increases or decreases, it does not affect the side lobe areas. Side lobe can be reduced only when ripples in stop band and pass band are attributed due to area under the side lobes. Side lobes can be only reduced if we use a window which does not have sharp discontinuity in time domain. In rectangular window, there is a sharp transition from 0, exactly at 0 it is 0, and exactly at 0 plus it is 1. then exactly at m minus 1 minus it is at 1 and m minus 1 plus it is at 0. There is a sharp transition due to which there are side lobes which have a very significant area under them. So they cause ripples in stop band and pass band. If we want to reduce those ripples, we will have to use the windows which does not have a sharp discontinuity. Thus they will have a side lobes with very small area. Another part to be seen in the frequency response is that there is an oscillatory behavior, and it comes with an oscillation and then it decreases down to stop band. So there is this frequency and there is an ideal response. So this oscillatory behavior which goes from the last maxima of the pass band to first maxima of the stop band will give an oscillatory phenomena called Gibbs phenomenon. As we increase the value of m, there will be sharp ripples. There will be very high frequency ripples, but at the edges it will again have the same kind of response, but in this case the transition will be much sharper. Again, if we increase the frequency further, it will reduce the ripples and then it will have a response like this. M is increased in a manner M, then red M, and then the maximum is blue M. But with the increment in M, that does not change this particular point which comes at the pass band edge or the stop band edge. This particular peak will be much sharper with the increment in M. Peak in the edge of pass band and stop band will be much sharper with the incrementing values of M. That's all for today. We'll discuss further topics in next lecture. Thank you.